Here we're going to take a look at an example where we calculate the molar mass of a gas based on the density of a gas using the ideal gas law. This is a pretty classic chemistry experiment that we are going to be covering here. This comes from another worked example in your OpenStax textbook. And it talks about a pretty straightforward experiment that can be done with pretty standard chemistry laboratory equipment where you can determine the molar mass of a volatile compound. Volatile compound is any chemical that transforms readily from the liquid phase to the gas phase just above room temperature. It's a chemical compound with a high vapor pressure. So the idea is you start by weighing out a mass of an unknown liquid in a closed container. Then you put the sealed container in a hot water bath so that the liquid inside the flask is vaporized and enters the gas phase. You make a determination of the mass of the vapor that it takes to fill the flask. Anything that doesn't fit inside the flask will have escaped through a little pinhole in your lid as the sample was heating up. And the idea is that if you heat the sample up carefully, just to the point where the entire liquid sample enters the gas phase, only the volatilized gas will still be sitting in the flask, and the mass of the recondensed liquid that you measure will be the mass of the liquid that it took to fill the flask once it had entered the gas phase. So the idea is you condense the gas of the unknown that pushed the atmospheric pressure out of the flask and then recondensed, and from that mass you can actually calculate the molar mass of the compound using the ideal gas law. This is a classical chemistry technique that was often used when you wanted to confirm the chemical identity of a product, because with careful experimental technique, you could verify what the molar mass of the pure liquid was. So here's our problem setup. Using this volatilization procedure, a sample of chloroform gas weighing 0.494 grams was collected at the end of the experiment in a flask with a volume of 129 cubic centimeters. Remembering back to Gen Chem 1, I hope it rings a bell that cubic centimeters is equivalent to a milliliter. So when you see 129 cubic centimeters, you can just read that as 129 milliliters. This data was collected at a temperature of 99.6 degrees Celsius. And the atmospheric pressure is 742.1 millimeters of mercury. If your flask was open to the atmosphere, and it was because there's a pinhole in the top of the aluminum foil, when the gas volatilized completely, the pressure of the gas inside the flask had to be equal to atmospheric pressure, and so we can take the atmospheric pressure to be the pressure inside the flask. We want to calculate the approximate molar mass of chloroform based on this experiment, and they're saying approximate here, hedging their bets, because this is a relatively crude determination of molar mass compared to modern chemistry instrumentation based methods. But with careful experimental technique, this experiment would actually give you a very good idea of chloroform's molar mass. Our strategy here is to remember that the molar mass of chloroform can be calculated by taking the mass of chloroform collected inside the flask and dividing by the number of moles of chloroform that were in the flask. We are going to be we can get the mass from the measurement at the end of the experiment, and we can calculate the number of moles of chloroform gas that it took to fill the flask from the ideal gas law. So we'll rearrange the ideal gas law to solve for n, the number of moles. N is equal to PV divided by RT. We know the mass of chloroform that it took to fill the flask, 0.494 grams. Dividing that mass by the number of moles it took to fill the flask will give the molecular weight of the chloroform. So collecting our variables here for a sec, mass is in 0.494 grams, units are grams, that's exactly what we want. The pressure is equal to 742 millimeters of mercury, but we'd like it in atmospheres if we're going to use the pressure variable in the ideal gas law. So 742.1 millimeters of mercury divided by 760 millimeters of mercury gives us the pressure in atmospheres. The pressure is 0.976 atmospheres. Similarly, the volume needs to be in liters if we want to input the volume into the ideal gas law. 129 cubic centimeters is the same as 129 milliliters. There are 1,000 milliliters in a liter, so the volume of our flask was 0.129 liters. The temperature at which the chloroform has been volatilized is the temperature of the boiling water. We just need it in Kelvin rather than in Celsius, so we have 99.6 plus 273 gives us 372.6 Kelvin as the temperature at which the chloroform was volatilized. We'll take the pressure, the volume, and the temperature, input them into the ideal gas law, and solve for the number of moles N. N is equal to PV divided by RT. So we have 0.976 atmospheres of pressure times 0.129 liters of volume divided by 0.0821 liter atmospheres per Kelvin mole as the gas constant. And we multiply that by 372.6 Kelvin as the temperature in the denominator. Everything divides out except for moles as the units in the gas constant, which is in the denominator of the denominator, which means it's actually in the numerator. So our final answer for the moles of chloroform that it took to fill the flask in the experiment is 0.004116 moles. We can calculate the molecular weight then by saying the 0.494 grams of chloroform that we weighed is equal to 0.004116 moles. If I take the mass and divide it by the equivalent number of moles, I can find the grams per mole for this compound or the molar mass, giving us as an unrounded answer 120.03 grams per mole as the molar mass of chloroform. We're entitled to 3 sig figs here based on our measurements, and we would report the molar mass at the end of this experiment as 120 grams per mole, which is a pretty good determination of chloroform's molar mass to 3 sig figs.